This is video number 17 in the course to prepare you for your Technician Class Amateur Radio license. In this video, we'll look at a number of electrical components along with how they are used. The test will have several questions asking you to identify certain components from a schematic diagram. Let's start by learning what a schematic diagram is, as well as what it doesn't do. A schematic diagram depicts electrical components by their symbols and how they are connected to each other. It does not show the physical layout, the size of the components, or wires links. In the following slides, I'll give you the name and purpose of the component, including information about that component and pictures of the component. There are a potential of 3 schematic diagrams on the test. The test will show the diagram and ask the name of one of the numbered components. There may be questions also about the component characteristics. Schematic 1 on the test has an unknown purpose since only a part of the circuit is shown. In Schematic 1, component number 1 is the power source. A power source can be either alternating current at a particular voltage or direct current. In this slide, it's going to be alternating current because there is a transformer involved. Component number 2 is a fuse. A fuse is made up of resistive material that gets hot and melts when the rated current draw is exceeded. Fuses are very important protection in case of a short circuit, which will let out the magic smoke in the device. We know that all electrical devices run on magic smoke because as soon as the smoke comes out, the device stops working with a grin. It's important to replace a fuse with one of the same value. And if a fuse blows, there's usually a reason. It's a good idea to find the reason before replacing the fuse. Component number 3 is a switch. The switch in this diagram is a single pole, single throw, meaning that it has 2 positions, on or off. There are a dozen or more types of switches as are noted in the slide. Component number 4 is a transformer. These devices have 2 capabilities. One is to isolate one circuit from another while transferring energy from one circuit to another circuit. Another is to either increase or decrease the voltage of the energy being transferred from the input circuit to the output circuit. Transformers also have a few different styles. The one in this diagram has an iron core, denoted by the 2 parallel lines in the middle of the transformer. Component number 5 is a diode. These are very useful components as they only allow current to flow in one direction. Current flows from the anode to the cathode, and the cathode end of the diode is marked with a stripe. I remember the direction since current flows alphabetically, A to C. As I said, diodes are very useful devices. However, if too much voltage is applied to the cathode, enough to exceed the breakdown voltage, the diode will short circuit and let out the magic smoke. The threshold voltage, which is the voltage at which current will begin to flow, depends upon the type of diode. Some more expensive diodes will begin passing current at about 0.3 volts. Others may be as high as 0.7 volts. Think of the threshold voltage as a kind of a dam across the input. Electrical current will pile up at the dam until there is enough voltage, that is pressure, to push the current across the dam. Component number 6 is a capacitor. As explained in an earlier video, a capacitor has 2 conductors separated by an insulator of some type. Again, applying voltages higher than the capacitor is rated for will cause the capacitor to break down, short circuit, and let out the magic smoke. As an aside, you'll notice that the capacitor in this diagram has current coming in from the diode, component number 5. And the other side of the capacitor is connected to ground. This capacitor will charge up because of the resistors, components 7 and 9, oppose the current flow from the diode. The capacitor will discharge when component number 10, a different kind of a diode, reaches its threshold voltage and passes the current through to ground. 1 farad of charge on a capacitor is a very large amount of power. The capacitors used in most electrical devices in the ham shack or around the home have much smaller capacitance, usually measured in microfarads, nanofarads, or even picofarads. The last bullet on this slide is a possible test question. If I'm measuring the resistance in a circuit and the amount of resistance increases over time, that means my voltmeter is charging up 1 or more capacitors in the circuit. When that happens, there's at least 1 capacitor in the circuit. That's the answer to the test question. Component number 7 is a resistor. Resistors restrict, but don't inhibit or stop the flow of current. They will use up some of the voltage, which is dissipated as heat. The stripes on the resistors in the picture are the code for the actual amount of resistance expressed in ohms in the resistor. Component number 8 is a light-emitting diode, a very specific type of a diode. Again, remember, diodes pass current only in one direction. The little lightning bolts next to the diode symbol are what tells me this is an LED, a light-emitting diode. Diodes pass current from the anode to the cathode. The cathode is usually the longer lead in an LED. Once the threshold is reached, usually about 0.3 volts, the LED will pass as much current as it gets as quickly as possible. So, any LED is always coupled together with a current limiting resistor. In this diagram, the current limiting resistor is component number 7. If that resistor isn't present, the LED will very quickly burn up and become a short circuit, once again letting out the magic smoke. Since LEDs emit light, they are mostly used as some kind of a visual indicator, such as indicating that the device is turned on. Component number 9 is a variable resistor, also known as a potentiometer. The outer 2 pins have a fixed amount of resistance between them. The middle pin, called the wiper, swipes between the 2 pins, and the resistance of the middle pin depends upon where the wiper is in relationship to the other 2 pins. Component number 10 on this schematic is a Schottky diode. This was the first semiconductor invented, and it absolutely revolutionized computers by replacing all the tubes in a computer with this very fast-acting diode as a switch. In a Schottky diode, current flows from the cathode to the anode, opposite of all other types of diodes. The little curly brackets at the cathode end of the diode is a clue that this is a Schottky diode. And that's all the components there are on schematic number 1. There are 5 components on schematic number 2. This circuit will turn on a lamp if some other part of the circuit, which isn't shown, draws current. Component number 1 is a symbol we've already seen. It's a resistor. In this case, a current limiting resistor to protect the transistor, component number 2, from being suddenly flooded with current. Component number 3 is a lamp, while number 4 is a battery. Component number 5 is a symbol for ground, which is the return path for current back to the source. Remember that current is never used up in a circuit, voltage is. All current entering a circuit must exit the circuit. Transistors are amazing little devices. They can function as a switch, they can modulate a signal, and they are excellent amplifiers. Transistors are made up of 2 slices of silicon interspersed with a different type of silicon. Transistors are amazing little devices. They can function as a switch, they can modulate a signal, and they are excellent amplifiers. Transistors are made up of two slices of silicon interspersed with a different kind of silicon. The silicon is doped by compounds that either strip electrons away, leaving so-called holes, making the piece of silicon positively charged, or by stripping away protons, making the piece of silicon negatively charged. Positively charged silicon is denoted as P material, while N material has the holes where the electrons are missing. That's a long and almost correct explanation of what P and N mean in the transistor type. The schematic symbol for an NPN transistor has the little emitter arrow pointing out, while an PNP transistor has it pointing in. I remember the types by not pointing in, NPN, or pointing in pointer, PNP. The slide explains how transistors are used, either as amplifiers or as switches. Note also that there is a special type of a transistor called a field effect transistor, or FET. Rather than switching or amplifying current, FETs switch or amplify voltage. The three pins on a regular transistor are the emitter, the base, and the collector. The three pins on an FET are the source, gate, and drain. Modern transceivers make extensive use of transistors as switches, modulators, and amplifiers. The final amplifier in a transmitter is the most expensive part of the transmitter, as it contains some very expensive power transistors to boost the output power from a few milliwatts to 100 watts or more. Schematic number 3 is a very useful circuit. It's a transmit, also called an antenna tuner. In this circuit, you can see the two variable capacitors and the tapped inductor that were in the antenna tuner I showed you in the video on antennas and feed lines. Symbol number 2 is a variable capacitor. It differs from the symbol for a normal capacitor by the arrow through the middle, denoting that the capacitance can be varied. Symbol number 3 is a variable inductor. Most of the time, this is a tapped inductor, although there are some variable inductors that use a wiper to vary the output impedance. And of course, component number 4 is the antenna. This slide repeats the information about inductors from the video on volts, amperes, ohms, henries, and farads. You'll notice there are several potential test questions about inductance. 1 Henry is a very large amount of power. In the electrical devices in our ham shacks and around the house, these will be much smaller inductors measured in millihenries and microhenries. This slide puts inductors and capacitors side by side to show how they are complementary to each other. In fact, they're quite opposite, which makes them very complementary. The main differences are how they store energy and how they release energy. Read through the information on both devices. If you still have questions, bring them up in the online class session. As I said, diodes are very useful devices, particularly for power supplies. A diode only lets current flow in one direction. In the top right diagram, alternating current is being fed into the circuit. The diode only allows the positive side of the circuit to pass and blocks the negative side. The resulting output is a series of pulsed direct current. If the input was 60 cycle current, the output will have 60 pulses of direct current, with the space in between each pulse. The bottom diagram employs 4 diodes to make what is called a full wave rectifier. The result is twice as many pulses of direct current. If the input was 60 cycle current, the output will be 120 cycle current with no space between each of the pulses. In either case, the next step in the power supply is to smooth out the rectified pulses of power. Combinations of capacitors and resistors, or capacitors and inductors, are used to do that. Since the capacitors are quite large in a power supply, be careful when working on a power supply after it has been turned off. The capacitors will still be charged, and touching one of them can deliver quite a shock. I have a, quote, Peter stick, unquote, named after the guy who showed me how to build and use it. It's simply a stick with a wire running up the stick and bare wire at the top end of the switch. The wire at the bottom end has an alligator clip on it. I connect the alligator clip to the chassis and then touch the bare wire at the end of the stick, which is a long ways from my hands, to the positive side of the capacitor and watch the spark. Then I do the same thing to the negative side. I even repeat it a couple of times to be certain the capacitors are fully discharged. There are some good things to know on this slide. Carbon zinc batteries, those are the normal AAA, AA, D, and C cells, are not rechargeable. Some of them will break down and possibly catch fire, put in a recharger, and left for a period of time. If a battery is rechargeable, it will say so on the battery. You'll need to know which materials are good conductors of electricity and which ones are good insulators. All wire, even gold wire, has some resistance. Electricity travels on the outer surface of the wire. Stranded wire has more outer surfaces. Heavier gauge wire has more outer surface than lighter gauge wire. The more surface area, the less total resistance and correspondingly less loss. It stands to reason that short lengths of wire have less loss than longer lengths of wire. There are several types of opposition to the flow of current, and all of them are measured in ohms. Impedance specifically refers to the opposition to the flow of alternating current. Remember when we talked about antennas and feed lines and the impedance of the radio and the antenna? Because radio waves are alternating current, the opposition to this current is impedance, and it is measured in ohms. Finally, how much power does your transceiver need? Remember that power is measured in watts, and in the video session on Ohm's law, I'll discuss the relationship of volts, amps, and watts. Essentially, volts times amps equals watts. If your radio needs 25 watts of power to operate efficiently, and you're feeding it with 12 volts from the battery in your car, you'll need 2.5 amps of power. The cigarette lighter in your car is built for about half an amp. If you connect your 25-watt input radio to the cigarette lighter, you'll burn up the wires in the lighter, letting out the car's magic smoke. Just don't do that. The power requirements of a transceiver are determined by how efficiently the transceiver is at using the input power, what the control and monitoring power requirements are, how efficient the power supply is, and by the way, a full wave rectifier is much more efficient than a half wave rectifier, but at about twice to 3 times the cost. And also how much power is going to be used up as heat. Modern transceivers are built for 12 volts of input power plus or minus 15%, or 1.7 volts. If the voltage drops below 10.3 volts or so, the transmitter will usually shut off. This concludes the video on electrical components and schematics. This is one of the longer videos as there are many components available to be used. There will be several test questions based on the material. I'd recommend reading the information through once again before taking the test. As usual, if you have any questions or concerns, please bring them up in the online class session or email them to me at rolandksmith@gmail.com. We'll see you online.